constant rate look like on a graph? So think about what we've done with slope. If our slope was 6, we would say we're going over 1, so we're going to grow 6. We're going over another 1, we're going to grow 6. We're going over 1, we're going to grow 6. Our growth is constant. What does that look like on a line? What are the characteristics of that line?
It's going to be steep.
It will be steep, but what more?
It'll be a straight line.
It'll be straight. Our constant growth means that we're growing at the same rate over time, so our growth is constant. So our line is going to be straight. Good.
Okay, so yes, that's called a linear function. We've already talked about these, and that's all we've worked with so far. When we're graphing equations, that's all we worked with so far. It's a linear function with slope, and it's a constant rate.
Linear is the focus of 8th grade pre-algebra. Linear. And you can see up there on the wall next to the clock that Wordle. Those are the 8th grade standards put in a Wordle. And the words that are the largest are actually the ones that show up the most. And what word is the biggest on that poster? Linear. Yeah, the 2 words, linear and equations, are the most repeated words in the 8th grade standards. If you did the same Wordle with the Algebra 1, like 9th grade standards, you would see different words because linear is not a focus in high school. Linear is a focus now.
Okay, so let's take a look at this equation. Y equals x squared. Have we worked with anything like this before?
No.
No. But let's try now. Let's see what we can do. We're going to make a table with coordinates that satisfy this equation. What can we do?
Now, you don't need to know, I'm sorry to cut you off, you don't need to use a slope and a y-intercept to graph a line, right? You could always just use coordinates. So here's how we can do that with the table.
-1 is x. Yeah, 1 is y.
-1 is x. Yeah, 1 is y. How did you know?
Because -1 times -1.
-1 times -1 positive 1. And that's what this symbol is telling us to do. It's telling us to multiply by itself. Multiply the x by itself. Right? So what's another coordinate we can have?
Who can give us another value for x so we can calculate our y?
Anything. I don't know.
3.
3.
And then 1 will be
And then
No.
y is
9.
Good. Who can give another one? It doesn't matter what value, really any value. If you're graphing like this, you can choose any x values. Who can give us another idea? Leo?
4. Minus 16. Right?
5.
Do you have to keep going up here? I mean,
You can go and then
yeah, so it doesn't have to be 5. Let's use a different number. We can use something else. All right, 2. Good.
What's the easiest number that we could put in there to find out
Mark
y?
it good.
0.
0. Yeah, if we put in 0, what are we going to get?
0.
0. Yeah. All right, so now we can use, we don't have to use like the y equals mx plus b formula. We can use these coordinates to graph this. So let's do it. How can we graph this?
What points can we plot?
-1.
-1 and 1. All right.
Positive 3.
Positive 3. And 1, 2, 3. Two and 4.
0,
0, 0. That's my favorite one.
What would you get if x was 1? If x is 1, y is 1. -2.
Four.
-2, y would be 4. What does this line look like? No. What does this line look like? What kind of shape? It looks like, what did you say? What letter did you say? Yeah, okay, so let's draw it. He's not wrong. It actually curves a little bit. So like a B, like a U.
Is this like anything we worked with before?
Oh, that's what the in the book.
There wasn't in the previous.
Is that linear?
No.
Yes.
It actually isn't.
Is that linear?
No.
No, why not?
But it's not straight.
So it's not straight. But looking at the table, how do you know it's not linear? What do you notice about our growth? So look at like from 2 to 3 and then from 3 to 4.
It's kind of like up and down.
Not necessarily different directions. I know we're in a weird order on the table, but imagine going from an x of 2 to an x of 3. What happened to your y's? And then look at your x of 3 to your x of 4. Look at your y's. What do you notice about the growth? It's different. Our growth is not, it's not constant. Our growth isn't constant. That is called a parabola. You don't need this yet. That's a parabola. That is like, we'll do that in the spring. Direct parabolas and quadratics in the spring.
Alright.
Okay, good.
Okay, so the graph of y equals x squared is not a linear function. So the graph is not a line. So let's look at another one. So now we have y equals x squared plus 2. So if you take a look at the table,
What they do.
what do they do here?
Look at the x values and look at the y values. What they do.
What do they do here?
What did they do that we just did?
How did they fill in that table?
We just did it on the previous slide.
How did they fill in that table? This is a blank table. What would you do to fill it in? All you had is this equation, y equals x squared plus 2. What could we do?
How do you get coordinates from the table? Leo, what'd you do? What would you do?
Well, they can choose any number,
Okay.
and since the equation is x, like double the same number of the x that they had.
Be careful. It's not double
Well, not double, like the same number, they multiply by the same
times itself.
and times itself. So -3 times itself would get 6. No wait, 9, and then they would add 2,
Good.
which would have gotten their y.
So they're substituting values. And I like how you started by saying any x value. You can really use any value. They chose to use some small ones.
So take a look at this graph. How is it different from the graph that we just did from the previous slide? How is this different?
The y-intercept is 2.
The y-intercept is 2, so how did that change it?
I took the whole graph and did what to it? It just moved it up. How many units?
What was
Yeah.
the y-intercept before?
0.
Yeah, the y-intercept was 0 before. So it started here. So it took the whole graph and just moved it up.
Perfect.
So give an example of an equation for a function that's not linear.
That is linear.
Oh, that is linear. Sorry, that is linear.
What was it?
Y equals 2.
Y equals 2x. Who can give another one? What else is linear?
Linear function.
Y equals 4x.
Y equals
y equals 6x. How about y equals 1/2 x minus 3? Linear? What about a line makes it linear? That's key here. Why is y equals 1/2 x minus 3 a straight line? Think about the growth. The growth of my line is what? Every 1x, I'm still increasing 1/2. So my growth over time is still constant. It's still constant. All that time that passes, it's still going to be a half. Good.
So you could graph a function, that's how you could tell how it's linear. How else could you tell? Like we have y equals 2x plus 1, we graphed it here, we find all this points, we graphed it, and we were like, oh yeah, that's a line. That's linear. How else can you tell besides just graphing it? How can you tell? What did we just say? Well, on the previous slide, we came up with all these equations and we said they're all linear. Why? Why were they linear? What
What
made
were you
them
saying?
linear?
Yeah, what were you just saying? How can you use the table to prove that it's linear?
Like how y is moving by the units and the x.
And it would have to be what for it to be linear? So you're saying you want to use the table to look at the movement, like the growth of the y and the x. And in order to say, yep, that's linear, or nope, that's not linear, what would the difference be in a table? What would you be looking for or trying to identify? Think about that. Think about, because it's easy in a picture, like when we graph it, it's really easy, like that's not a straight line, right? But you're not always just going to be given the graph. Most of the time you'll be given the equation or the table. So think about as we move to the next example, what about the table proves to you that a line would be straight or not straight?
Well, what about the equation? What about the equation? How can we look at an equation and see if it's linear? What made all those equations on the previous slide linear?
They go at a constant rate.
They go at a constant rate. How do you know? How do you know this is at a constant rate before you graph it? Without graphing it. How do we know this equation right here, y equals 2x plus 1. How do you know that's going to go at a constant rate?
It's multiplying every x value by 2.
Yeah, it's multiplying every x value by 2. So every time you go over 1, or
You'll grow another 2.
1x, you'll grow another 2. every single time you grow 1x, you're gonna grow 2. 1x, you're gonna grow 2. It's always gonna be constant, so it's gonna be a straight line. 1x, grow 2. Okay. All right, so let's figure out the function y equals x cubed is linear. So let's take a look. We have our x values right here for us in a table. How can we get our y values? We have this equation y equals x cubed. What can we do to find our y values?
Multiply itself by 3. So -2
That gives us
So -2 times -2 times -2, -8. How about -1? -1 times -1 times -1, -1. How about 0? 0. How about 1? 1. And how about 2? 8. So let's plot these points.
how we plot these. How we plot these.
What coordinates do you want to put down?
-2. -2, -8. -1 and 1 and -1. 0, 0,
One and one.
1 and 1. Two over. What does this look like? Is this linear? What do we know?
It's not a constant rate, it's not a straight line.
Yeah, it's not a constant rate, it's not a straight line, it actually kind of looks like this. How do we know looking at the table? Because it's not going to be linear. We know looking at the graph, we just plotted all those points, and we know if the graph that's not linear. How do we know about looking at the table?
Because did you like for x, it's going by 1, and y, it goes by 7, then it goes by 1.
So this is going by 1, we're adding 1 every time. This is going, instead, adding 7 here, and then what are we doing here? We're adding 1 here, and what are we doing here? Adding 1, then what are we doing? Adding 7. So is that constant?
So in the picture, it's really obvious that it's curved, but in the table, and you were saying it before, you just couldn't get those words out. The growth in the table is what? It's different. Yeah, each unit is kind of different.
Yeah, every 1 unit, we're not going just 7 or just 1, or it's not going by a constant rate. We're adding 7 here, we're adding 1 here, it's different each time. Okay, so now let's take a look at y equals 2 plus 1 and y equals x cubed. Are these equations similar?
So we can look at a graph and we can tell if one is straight and one is curved. Right? We can pretty much look at a table and figure out the same thing. Now we're going to try to figure it out just by utilizing an equation. So we know that the equation on the left is what kind of line? Straight. And we know the equation on the right is what? Curved, not straight. Okay. So let's start to talk about their differences and their similarities, because you're going to be able to determine by just looking at an equation if one is going to be straight or curved after we go over these comparisons and differences. Okay. How are they similar? What about them is similar?
X is being multiplied by something.
Okay. Both are multiplying the variable. So there's some kind of growth. Any other similarities you see? How about differences? How are they different?
The one on the left is multiplying by 2 then adding by 1, and the one on the right is actually cube. Whatever you plug in for x is cubed.
Alright, so whatever you plug in for x is cubed over here. And then over there, it's being multiplied and then added.
So different calculations. What else do you notice that's different about them? Just by looking at them. This isn't a trick question. So it's not written, but if it's not written, it would be assumed that it would be 0. That's a good point, though. The y-intercept isn't as obvious. But without doing any type of manipulation with the equations, just look at them. What do you see that's different? Not a trick question.
So we've worked with equations that look a lot like this up until now. What's different about this equation than the equations we've been working with?
There's an exponent.
There's an exponent, yay! There's an exponent here. So what does that tell us?
Think about what an exponent represents, right? Like in the first one, like I know we're multiplying by 2. So like no matter what the number is, it's like double it, we're gonna double it, we're gonna double it, we're gonna double it. if you're cubing a number or squaring a number, are you always multiplying it by the same amount? So like if x is 1 and x is 2 and x is 3 and x is 4, are you always going to be performing a multiplication operation by multiplying the same number? Like in this one, you're going to multiply by 2, and then you're going to multiply by 2, and then you're going to multiply by 2. Why not? What does that exponent tell you to multiply by? Itself, the input. So the input in that exponent problem, the input actually determines what you're going to calculate, what you're going to multiply. Which means our growth is going to be what? It's going to be different, right? It's not going to be the same. Okay. So now you can make the connection.
So how are these graphs different?
But both the points are mainly on the quadrant of the second quadrant, I think, and the third or fourth.
First.
This one,
Yeah, like
the first quadrant?
yeah, the top right.
Okay, but
Primarily first and third quadrant. Okay. That's a good similarity.
what else is similar? Yeah, they increase and they decrease, both of them. Well, that means
Depending on the way you look.
yeah, depending on how you're looking at it, yeah.
There's more differences than similarities here.
So what are some differences?
The x equals x. 3 crosses the x-axis and 0, and the other one crosses it on 1.
The y-axis. So for the x cubed, it goes to the origin. And then for this one, the y-intercept is what? 1.
What's the biggest difference?
What's the biggest difference here?
The left one is a straight line, and the right one.
Good, yeah, the one on the left is a straight line, and the one on the right is not a straight line. So can you now make the connection between an equation, a table, and a graph, and what would make it straight versus what would make it not straight? The key is in what? Straight line versus not a straight line. The key is with the rate, right? If the rate of growth is constant, then it'll be a straight line. If the rate of growth is inconsistent in any way, your line won't be straight.
So what makes the rate of growth constant? Take a look. What do you think makes the rate of growth? What makes this a constant rate?
The slope of 2.
Alright, there's a slope of 2.
And what makes the one on the right not constant? But what is it in that equation that makes it different? The exponent, absolutely. The exponent is what's going to change your growth rate. It's not going to be constant.
Okay, oh, we got graph paper.
Yes.
So we're handing out graph paper. What you're going to do is graph these equations that are on the board.
So this is twofold because you are working on determining if something is linear or nonlinear, right? You may be able to look at the equations and know which ones will be straight lines and which ones won't be. But we also do want to reinforce and practice our graphing. You do not always need a y-intercept and a slope. Sometimes you may just want to utilize coordinates, like the tables that we did before. Okay, both methods are going to be helpful.